Greetings, my name is Professor Duke Orata. We are continuing our lectures in thermodynamics. And remember the last lecture we talked about heat transfers involving phase transformations. So I humbly request you to go through some of these things so that we build up. Today we want to develop those equations which we can use to calculate the boundary layer thickness, the thickness of that boundary layer. And we had said that the Nusselt number was x over sigma. And remember this, we simply got from the fact that we had h was k over sigma. So if we multiply by L over k, then that was the Nusselt number. So that cancelled. So we had L over sigma, and that L is x, is just a characteristic dimension. Now, let us just look at a schematic of that process. We have y, we have x. That boundary, called that sigma. We had indicated amount of fluid. We had looked at this segment here. That y, liquid film, m plus dm, and of course the velocity profile. This was our velocity profile. Call it u. This is dm. So we had this schematic. Of course, you notice at the top of the plate, the sigma, that is the thickness, that boundary is zero. Now, this volume element, its movement, in other words, its velocity, is dependent on the complementarity of the balanced activity between viscous forces and gravitational forces. And as we had mentioned, hydrostatic pressure and inertia forces are, even if they could be there, they play very minimal role in terms of movement of this element here, which we have indicated. So let's say that the movement, the volume element, is due to complementarity, balanced complementarity between viscous forces. In this case, we are talking about shear stress, shear force, better term, and gravitational force. So we are saying that inertia and hydrostatic pressures are probably there, but they are not dominant or playing significant role. Hydrostatic pressure and inertia forces not playing dominant role. So, we can now work with that premise in terms of the balanced forces acting on that volume element, So let us build this into some expressions. So we have talked of shear forces, and you know that the shear force, that is the dynamic viscosity. And you're saying it's working in consonant with gravitational forces. And when we talked about buoyancy force, we talked of that is density, volume, gravitational. That's density, volume, and acceleration. So that for the volume element here, that is of length, where we have sigma minus y, and the rest are unit dimensions, we can represent that as mu u dy dx. We have forgotten dx here, and we have forgotten dx there. Dy dx is rho. That length there is sigma minus y dx. And so simple rearrangement of these quantities, our g is there, on rearrangement and simplification, of course, the dx's definitely will cancel out. So we have mu, we have du over dy is rho g over mu sigma minus y. And so cross multiplying, we have du is equals to rho g mu sigma minus y dy. So if we integrate this quantity from y is equals to 0 to y, don't forget our diagram here, always think about it, because as we are talking, we'll be referring to it. The assuming boundary conditions y is equals to 0 to y. Let me just draw that diagram. I want it to be in your mind throughout as you're working, so that we are not left talking about something and it looks strange. Don't forget, let me just draw them. M. We have our velocity profile. Don't forget this diagram. As you are talking, always have it in your mind. That is, of course, liquid film. Now, so what do we have? So the integral to y du is equals to g over dynamic viscosity sigma dy 0 y. So we just use the simple integral calculus identity which we are used to. It's xn plus 1. See, so our life is easy. We have u is equals to rho g mu integral from 0 to y of sigma dy minus integral from 0 to y of y dy. So using that identity, so we have u will be rho g of dynamic viscosity into sigma y. Remember, where we have sigma 0 is 0, so that we have sigma y minus y squared over 2. Y squared over 2. This is the expression for the velocity profile. That is the velocity profile. That is the expression for it. And we are used to it. We already know that we have seen several parabolic forms accounting for the various boundary layers. Now, when the fluid flows through that segment, when the fluid flows through the segment, we will notice that there's a difference between the outflow and the inflow. And that difference, dm, is most likely the condensed vapor. It's most likely the condensed vapor. So when the fluid inflows to the segment M, the outflow difference is representative of the condensed fluid. Condensed vapor. Very important for you to get that point. That difference is most likely the condensed vapor. Now, how do you get the amount? That amount, dm, is basically the density, integrate the density and the velocity. This is the continuity equation, which we have talked about quite extensively in several of our lectures, and I keep encouraging you to look at them. And one way in which you always remember in all those lectures, I've told you that it's good to do dimension analysis to show that you're talking about amount. And of course, the moment you see density, that's mass over volume. So amount is there, mass is there. Always remember that. And so if it is from y, 0 to sigma, then in that particular case, we will have the integral 0 to sigma of rho into the expression for the velocity which we have here, g over mu into sigma y minus y squared over 2. And so let us work that expression there and see what we get. And like I always tell you, you must rationalize what you get. Whatever expressions you get must be consistent with what explanations you're giving for that particular system. dy. So let us get the quantities. So dm will be rho squared g over mu integral from 0 to sigma of sigma y minus y squared over 2 dy. Because if we carry out that particular integration, we have dm will be rho squared g mu. The integral of that will be sigma y squared sigma 0 minus y cubed over 6 0. Let's move that for now. So let's open up these quantities here. So we have dm rho squared g mu into, remember that's y squared over 2, we had forgotten that, y squared over 2. So that would be sigma cubed over 2 minus sigma cubed over 6. So of course, if we take the lowest common denominator, our system here, we have 3 sigma cubed minus sigma cubed. And of course, don't forget sigma is thickness. Don't forget, always remember the actual meaning of that particular symbol you're dealing with. Otherwise, it becomes very abstract. Then you lose track of what you're doing. So dm is equals to rho squared sigma over mu. This now becomes 2 sigma cubed. That cancels that, so we have over 3. We are getting there. So we have just opened up our system. Just open up simple integration, just introducing integral calculus, which you are now familiar with. We keep working with them and we still continue working with them. But now we have this quantity here, which you can simplify. Remember, note the integral of x squared dx is x cubed over 3 plus c. So using this identity, I can transform this quantity using that identity. So that what do we have here? Therefore, dm can be expressed as rho squared g over mu, and I use this identity to transform that so that I have there as sigma squared d sigma will be sigma cubed over 3. Don't forget, I've just used the identity here. If you integrate that, you get x cubed over 3. So my x, replace your x with sigma. So I can replace that and have that now as x squared dx when I integrate those quantities. Integrate the quantities. I'll have the same expression, which we have. They are very important for us to note that that's just an identity which we have used. So let's not be in a hurry to work with it. I'm just showing you that. Now, keeping this in abeyance, we have just said that that difference dm is most likely the condensed vapor. And during the condensation, there's a latent heat associated with that process of condensation. There's latent heat. Associated with the condensation. And that is the heat which is transferred to the wall. That is the heat which is transferred to the wall via conduction. Remember that. Via conduction. We had vertical streamlines. And we say that that heat is transferred the wall. It is not convective. It is a conduction. It's a conduction. Because remember, even the vapor and the film surface are almost at about the same temperature. Now, but inside we had said that the temperature drops. The temperature drops significantly to the saturated, significantly below the saturated temperature. If you remember, if you look at our first schematic, just I encourage you go back through our lectures, see the first schematic where we had the temperature wall and we had the saturated temperature. Now, so what are we saying? So that latent heat, the latent heat, we can represent that as HF. dm. HF dm. Remember that? And that is Q, which is minus K dx theta over sigma. Remember that that is from Fourier's heat law. From Fourier's heat law. And now we have a dm there, so we have HFG for that condensation. Yeah, will be minus K dx theta over sigma. We can now remove this. Is equals to rho squared G over mu sigma squared d sigma. Sigma squared d sigma. And so, working with these particular quantities here, we have minus K. So on simplification, we can take the K down, can cross multiply the K's, can cross multiply the sigmas, can cross multiply this theta. So we have dx will be equal to rho squared G over mu K, and we have theta, K and theta, and what have we done? So we have sorted that out. We have sorted that out, sigma. So we have sigma cubed d sigma. We have sorted out basically everything. Theta sorted out, K sorted out, sigma sorted out. So what we have is this. These quantities. And so when we are dealing these particular quantities, if we integrate from 0, we have 0 to x, integrate these quantities. So we'll have x here as equals to rho squared G mu K theta sigma power 4 mu K theta. 4 mu K theta as our value here. And so we now go back to our quantities. We are making progress. So sigma, that is the thickness, remember, sigma to the power 4, so on rearrangement, so we can rearrange so that we have sigma, the power 4, will be equal to 4 mu K theta x, just cross multiplying, divided by rho squared G. And so basically sigma will be the fourth root that. But remember, we say that now we have computed sigma. We have computed the value for sigma. And so when we have it in the Nusselt, guess you had said it was x over sigma. X over sigma. So we can plug in this value to this particular system here. You can put that, you can plug in that value, that would be x can have it as, let's call this quantity, let's call it y. Let's just call it y, so that you don't go carrying these bulky things. That's x over y. So now we are able to compute the thickness boundary. And now we can completely compute the Nusselt number. Because we know the dimensions, we have the dimensions. Now we have the expression for the boundary thickness of that boundary layer. And so when we are dealing with these issues, the fundamental principle there is to realize that in most of these heat transfers, there could be phase transformation. And if there's phase transformation, you have to account for that phase transformation. And you have to be able to figure out what are the forces in play in that particular system. And when you have all those information, you also have the latent heat associated with those phase transformations, then you are able to come up with this expression so that you're able to compute the boundary layer. And once you've computed the boundary layer, you can compute the Nusselt number. Very, very easy. And of course, the transfer coefficient, remember, H, we had said was K over sigma. And that K over K was simply thermoconductivity. So you can, because you now can calculate sigma, you can calculate the transfer coefficient. So let's stop at that point. We are continuing with our lectures.